for your patience. And I'm going to introduce our speaker, Dr. Jessica Kapp, and she is the Associate Head and Senior Lecturer in our Geosciences Department. She earned her Master's in Geology from Vanderbilt University and her PhD at UCLA. And she came to Tucson. Her husband was offered a job at the University of Arizona, and she taught school, math and science for 2 years, and then became part of the faculty in the Geosciences Department. In addition to her passion for geosciences, she's a blogger, a runner, and the author of a memoir about her field experiences in Tibet and several works of fiction. She was actually a featured author on our Science Cafe last year in Science City, which was great. We'll have her come up and give her presentation. Following that, we'll have a question and answer session, and Jessica said she'd make herself available one-on-one if your question didn't get answered for a bit of time afterwards. So without further ado, Jessica.
Thank you so much. Can everybody hear me? Okay, thank you for having me. It's such a pleasure to be here. We are going to jump right in. Geologic time is real and it's deep, and there's a lot of it, so we're going to get started. So those of you who came to Dr. Fleming's talk last month, remember that he took the idea of cosmic time from the beginning of everything as we know it, everything, time, space, which we call the Big Bang, which was the origin of everything, and he put it onto a calendar year. Sort of give us a feel for what that means. What is the immensity of time, cosmic time? And if you remember, he talked about the formation of the solar system happening here early in the month of September. And so tonight we're going to focus on the geologic time scale, which really happens from that formation of the solar system. Earth is part of our solar system, and so it formed as the solar system did, and work our way down to recent time and to man and the very small portion of the time scale that man takes up on the geologic time scale. And we're not going to have time to go through every single event that's happened, but we're going to talk about how it is that geologists have been able to work out the geologic time scale and put actual numbers on the time scale, ages for geologic events. So we have to start by looking at the geologic time scale. Now, sometimes when you first see this, it's overwhelming. There's a lot of information on the geologic time scale. And I teach this in a historical geology class, and one of the first things I tell my students is, I don't expect you to memorize everything on this time scale. There's so much stuff on the time scale. But I want to draw your attention to a few things that we're going to talk about this evening. And the first is that we see these names on the time scale. And these names, of course, are the geologic eras, and they're the geologic periods, and down to the epochs and even the ages. And those names are defined by life and life events that have happened on Earth. Okay, and so geologists have taken a really close look at the fossil record, and they've been able to see places in the geologic record, in the rock layers, where life has changed in some way. And that's where we see boundaries between these names. Okay, so that's the first thing to keep in mind. We're going to start there in just a slide or two. The second thing is that we can see numbers on the geologic time scale. And I know the numbers themselves are hard to see, but those numbers are actual numeric ages. And they're ages that we've calculated that we have really good constraint on. And so where did those numbers come from? We're going to talk about that as well. And then the last thing is to notice these black and white bars here on the sort of middle to late portion of the geologic time scale. And those represent magnetic reversals that have happened in Earth's magnetic field, where what today is north at the North Pole was actually south, and it has reversed many times throughout Earth history. And that becomes important because that is how we started to understand that the Earth's surface is dynamic. In other words, it was our jumping off point for the plate tectonic theory, which is the unifying theory of geology, right? If we don't understand plate tectonics and the fact that the Earth moves and changes, then we don't understand anything that we're seeing happening on Earth today. So those are the things we're going to focus on today. Some of the eras that we're going to talk about, the Paleozoic, the Mesozoic, and the Cenozoic, these names, again, relate to life. Paleozoic means old life, Mesozoic means middle life, and Cenozoic means new life. And this number here of 541 million years ago is an important number because that's when life on Earth exploded and diversified. And the rocks before that time don't have a lot of fossils, and the rocks after that time do. And so we're able to get a lot more information about life in rocks that happened after that 540 MA boundary. And we'll talk about that a little bit as well. So how did we get a handle on the age of the Earth? Well, of course, lots of people had ideas about the age of the Earth. And as you can imagine, before the science, people relied on the Bible to tell them how old the Earth was. And in particular, there was this guy, Bishop James Ussher, who was an Irish archbishop. And he was one of the first people to adopt a very literal interpretation of the Bible. And in particular, he looked, to the first book of the Bible, the book of Genesis, and he sort of reconstructed what he considered to be the genealogy of the people in the Bible. And he came up with what he thought was a very accurate and very precise age of the Earth that was roughly 6,000 years. In other words, that God created the Earth in 6 days, 4004 BC, okay, which would have made the Earth about 6,000 years old. Now, I want to just say that this is a testament to the power of religious thinking and the power of the Bible, in that we looked at a Gallup poll from 2014 where people in this country were asked, what do you think the age of the Earth is? And 42% of Americans still believe that the Earth is less than 10,000 years old. So that's how far we've come since Bishop Ussher, okay? But we actually have come pretty far. We have come pretty far because now we actually know what the age of the Earth is. And it started when scientists started to say, let's bring some logic and science into this. Let's start to really decipher what's going on the Earth. And so it started with simple observation, which is the way all science works, right? It all starts with an observation. So I'm going to ask you to make an observation. I want you to look at these pictures, picture A on the left and B on the right. And I'm going to ask you, what differences, if any, do you see between the two pictures? The sandbar, yeah. This is the first one to jump out. There's the sandbar here. Well, it's here in picture B, but it's covered by vegetation. So the vegetation has grown a lot. Okay. Any other differences that jump out at you? The width of the river. Okay, so maybe there's more water in the picture to the left than to the right, and that's actually the case, drought conditions. Okay. Yeah, so the mountains have weathered down a little bit. Okay. The main thing I wanted you to notice, though, is that in general, not much has changed with the rocks, right? So the river might be wider or narrower, the trees have grown or disappeared, there might be a few features on the surface that have weathered down, but we can see very prominent geologic layers. For example, this one, which is here in this picture, it hasn't gone anywhere, right? The basics of the layers have not changed, and this is about a century apart. This is a picture taken of the Green River and the Canyonlands about a century apart from the same location, okay? So what does that tell you? Well, what it told James Hutton, who was a scientist back in the 18th century, is that the things that happen on Earth geologically happen very slowly. And this was a key concept, because that means that the Earth can't be young. It has to be old, because it takes thousands to millions of years for real geologic change to be affected at Earth's surface. Okay, so he was sort of the father of the modern concept of geologic time. The Earth has to be old, and there were a couple of things that he asserted. One is that the Earth's surface should be completely flat. It should be worn completely flat by erosion, but it's not. And so that means there's something happening on Earth that's renewing Earth's surface, that's growing mountains and building things. Okay, so he was one of the first to really make that observation and realize that the Earth was dynamic. But the second thing that he asserted, and this is really important, is that geologic processes are slow, and that the processes happening on Earth today are the same exact ones that were happening in the past. Things like weathering and erosion and breakdown of rocks, the transport of rocks, those things were happening thousands of years ago, millions of years ago, possibly billions of years ago. And that concept he called uniformitarianism. This is the idea that the present is the key to the past. So what we see happening on Earth today was happening in the past as well. And that was really, really key. Now, in order to make observations about rocks and put them in order, So this is the simplest way to kind of do things, is to try to figure out what came first, what came second, and what came third. We have to understand some basic geologic principles. So this is some nuts and bolts geology to get us started. And we call this relative dating. So this is one technique for getting at geologic time, is to put things in order. It doesn't give us a numerical age, but it gives us an order of events. And so here are some of the very basic geologic rules that we have to know. And the first one is the simplest one, which is that rocks, when they're laid down, so sedimentary rocks, are laid down flat and horizontal. And that's what we call original horizontality. Now you can imagine this in a river. As it's flowing, it's carrying sand grains and pebbles and things in the water. And those materials, if they settle out, they're going to settle straight down, right, onto the bottom of the riverbed. And over time, you're going to get a buildup like a layer cake of those layers. Now, those layers can't form vertically. They have to form flat, like pancakes. And so that's a very basic principle that we have to assume is true, and we know that it's true. Well, that also means then that the material on the bottom of those layers had to be laid down first, and so it's the oldest. And as we work our way up, we get to the younger material at the top. So right there, we've already got an age constraint. It's very basic age constraint, but we know where the older material is and where the younger material is. So that's great. The other thing that we know is that if we see rocks that are not laid down flat, and we do a lot of the time, we go out into the field and we see rocks that are upended like this, well, that tilting of those rock layers had to happen after the rocks were deposited. So that has to be a younger feature. So that's another way to get a time constraint. One of the other rules that we use in the field in particular is what we call cross-cutting relationships. And this is where we see layers of rock and they're cut by something. It could be a magmatic intrusion that cuts across the layers. It could be something that we call a fault, where the layers have a crack through them, a break, and the rocks have moved on either side. And what we know is that those layers were there first, and the cross-cutting feature has to be younger. So that's another relative dating principle that we use. And then finally, we use a principle called inclusion. And this means that sometimes we have younger material, like say a magmatic rock, that picks up and incorporates older stuff that was laying around. It was already there. And so the inclusions, the material that was picked up, has to be older than the material that surrounds it. Okay, so that's the third really important principle. Now we can look at this in animation form. This is kind of fun. And we can see how this works. Let's hope that this is going to work. We tried it and it did. Okay, good. There we go. So what we're going to see here is a series of geologic events that are going to happen in order. So the first is our very basic deposition of layers. There's one layer, maybe another layer comes in on top, maybe a siltstone, and then maybe a sandstone. And now we've got our flat horizontal layers. Now there's our cross. Oh, I thought I hit pause. Sorry, let's go back. Went a little bit faster than I was talking. Okay, so now we're going to get a cross-cutting relationship where we have a magmatic intrusion. That's a magma that comes in from underneath and cuts into those existing layers. So that magma has to be younger. And then we're going to have some tilting which occurs. Now that usually occurs because of plate tectonics, something that's building mountains on Earth and causing the layers to tilt. So that's even younger. Now we're going to have some erosion that takes materials away. Now imagine that. Imagine being a geologist in the field and there's a bunch of stuff missing. There's layers that we think should be there, but they're not. Well, that tells us something too. That tells us that there was erosion. And that's something that we can also identify as we work in the field. And then we may get deposition of new layers on top. And so we end up with a very coherent and clear geologic picture of all of these different items together. And that boundary where we had erosion and then new deposition on top has a name, and we call it an unconformity. And when we find one in the geologic record, it tells us that there's some missing time, which is really important. Okay, so let's go back to this. I'm just realizing that my microphone's making some noise. Sorry about that. I'll try to keep that to a minimum. Okay, so James Hutton, who was the father of geologic time, he took a bunch of people to this location in Scotland called Sychar Point. It is an amazing geologic outcrop. It's a pretty small area that shows an abundance of geologic evidence of activity. Now, when you look at this as a non-geologist, it may just look like a bunch of grungy rocks, and you don't see a lot going on in this picture. But one thing you might notice right away is that some of the rock layers appear to be vertical, right? They're upright, they're tilted. and some of the rock layers are not. So right there, we know that there's multiple geologic events going on. Okay. So let's break this down. So we know that initially, these rocks couldn't have been laid down vertically. They had to be laid down flat. So that's our first geologic event, was deposition. And then we see that the rocks are upright. They're vertical. So something had to either bend them or fold them or tilt them to make them not flat anymore. So that's a second geologic event. Then we have erosion. Now we can tell that because these vertical layers sort of truncate into this surface. They disappear, and then we have new rock layers on top. So that's our fourth geologic event, is deposition on top of our erosion. And then finally, this whole thing had to be tilted because those top layers are not flat anymore, right? They're tilted off to the left. So just in this one location, Hutton showed his students and his colleagues, look at, there are 5 different geologic events here, and every single one of them took at least thousands of years to happen, if not millions of years. These things don't happen fast. Well, if that's the case, the Earth can't be 6,000 years old. It has to be older to accommodate all of these different events. So how many of you Grand Canyon? Quite a few. Okay. So if you've ever been to the Grand Canyon and hiked the Bright Angel Trail, when you look across the canyon, you can see a very prominent geologic feature that we call the Great Unconformity. And remember, an unconformity shows us there's missing time, right? Something's been eroded away. Well, here it is in the Grand Canyon. Can anyone see it? Can you pick it out? Yeah, so the difference here is that we have layers. Oops, I just showed you the answer. Darn it. Okay. I meant to click my point, but it didn't work. So here are the layers underneath that are a little bit, and they truncate at this very flat layer here, which is the Bright Angel Shale. And so there's our unconformity between the two. Now, what's amazing about the Great Unconformity is that it represents about 1 billion years of missing geologic time. Isn't that nuts? So layers down here in this, what we call the Grand Canyon supergroup, have a cross-cutting relationship. There's a granite that intrudes them that's 1.4 billion years old. And then the first layer above the unconformity, which is called the Tapeats sandstone, is about 500 million years old, 540-ish, right? When life exploded, became really diverse. There's about 1 billion missing years in there. Okay, so a lot of erosion that happened, and maybe non-deposition that was going on during that time. But if you have hiked down to the plateau point, which is that point where you look out across the canyon and you can see the river down below, just look down under your feet and you're going to see an abundance of fossils in the rock. You cannot miss them. And that is the recording of that, what we call the Cambrian Explosion. That's that explosion of life where things get really diverse, and there's all sorts of critters in the oceans that now have shells and hard parts, which makes them preservable. They get preserved in the rock record. So that's a really amazing thing that we can see in the Grand Canyon. And if we look at a sort of cartoonish cross-section of the Grand Canyon, there it is. There's these tilted rocks below of the Grand Canyon supergroup. There's that 1.4 billion year old granite that cuts in, erosion along this surface right here, and then there's our nice thick stack of sedimentary rocks that get laid down on top of that unconformity. Now, so we've got our relative time rules that we have to follow to get ages, but we need a better constraint than that. We can go out in the field and say this is older than this, is older than this, but that doesn't give us any ages per se. So one of the first ways that geologists started to put the words on the time scale and to make some divisions was to look at fossils. Fossils show differences in life. And so we call the fossils that we use to give us these divisions index fossils. And these are fossils that exist over a pretty narrow period of time, but are globally distributed. So we can find them in rocks all around the Earth. And that's good because then we can correlate those rocks, different time periods in all different locations. So for example, if you find rocks that have trilobites in them, if you want to see trilobites, go to Flandreau. They have a trilobites exhibit right now. If you find rocks with trilobites in them, you know that you're in this early portion of the Paleozoic era, either the Cambrian or Ordovician time period, and that's global, okay? So you see, we started to see differences in life. Now those things disappear, and then as we move up through the time scale, we see all sorts of different critters appearing that weren't there before. The middle period, the Mesozoic, this is the age of the dinosaurs. And so rocks that have dinosaur fossils in them have to come from this geologic era. There's no other time in geologic history where dinosaurs existed. So that's how we start to make our time scale make some sense. But it gets even better than that. We want to start putting some numbers on our time scale, right? We don't want to just have relative time. So I'm going to take this necklace off because I think it's screwing up my microphone. Is it distracting? No, it's bothering me. So I'm going to do it anyway. All right. I'm just that kind of person. Okay. Major scientific breakthrough was radioactivity. Okay, how many of you have heard of radioactivity? We've all heard of it, right? Right. How many of you understand it and how it works? Oh, some of you do. Okay, good, good, good. Well, I did my PhD on dating materials and using radioactivity to date materials, and I don't fully understand radioactivity, but it's really important in order for us to get ages of Earth materials. So a little bit of history, just because it's fun, and because Marie Curie is one of my favorite scientists of all time. When you think of radioactivity, you think of the Curies, right? I mean, these two really were the ones who defined radioactivity. They weren't the first to discover it, by the way, but they were the ones who basically walked around their lab with radioactive materials in their pockets, and that's how crazy they were, because they wanted to understand radioactive materials. Marie Curie actually discovered 2 new radioactive materials, radium and polonium, and she's known for having vials of radium just stuck in her lab coat and just working with it. Her husband, he was even crazier. He took a chunk of the stuff and taped it to his arm. I don't know why, but he did it. He had it on his arm for about 10 hours, and when he took it off, he had radiation burns. He didn't know what they were. He thought he had found a cure for skin cancer. I mean, come on, right? These are smart people, but they didn't understand it at the time. This was brand new. Well, Marie Curie was the first woman to win a Nobel Prize and the first person to win 2 for her work on radioactivity. And if you want to see her notebooks, you can. They're in a lead-lined safety box in the National Museum in Paris because they're still radioactive. Because she was just awash in this stuff. You know, their lab, they just had it out. They would just be working on it. It was everywhere. And of course, she died pretty young from complications from radiation exposure. But if we didn't know about radioactivity, we would never have been able to come up with a clock to measure geologic materials, how old they are. And it was also the work of Ernest Rutherford, who was a physicist, the father of nuclear physics. He deciphered the structure of the atom. He was the one to tell us what the atomic structure was like, that there was a nucleus with protons and neutrons and these little electrons buzzing around. And if it wasn't for that, we knew that radioactivity existed, but we wouldn't have really understood what that meant and how it worked. Well, now we do. And what we know is that radioactive elements, what we call isotopes, radioactive isotopes, they go through radioactive, what we call decay, because they're unstable. These are isotopes that the nuclei of the atoms are not happy. They're unstable, they're energetic, and they're trying to get to a more stable state. And they do that through many different ways. They either give off subatomic particles like protons, neutrons, or they absorb them like electrons. And that changes the structure of the atom, which means it can change what element it actually is. Okay? I know that seems a little vague right now, but let's think about this in some sort of simple terms. The unstable isotope we call the parent. That makes sense, right? The parents are always unstable. And the stable result we call the daughter. Okay? That makes sense. So here's an example. Potassium, which is an element we all know and love, is radioactive. It decays. It's unstable. It's unhappy being potassium-40. And it decays into another element called argon. It changes naturally into argon through radioactive decay. Now, why do we care about this? We care because if you think about an earth material, say a mineral, and it has potassium in it. Most minerals, when they form from a magma, right, which is a melt. It's a liquid rock. Well, then it solidifies, and now in that solidified mineral, we've got a bunch of potassium. And over time, it's going to decay into argon. We can take that mineral and we can extract the potassium that's left over, the argon that's been created, and we can calculate how long it's been since that started happening, which is when it formed, which is a geologic age, right? Now, in order to do that, we have to know how long it takes for potassium to decay to argon and how much decays over what period of time. Otherwise, we don't have that time element. Well, it turns out that we do know. A bunch of scientists back in the 1940s figured out that you could measure something called a half-life. That is the time it takes for half of the unstable parents to decay into stable daughters. Now, it turns out that these are constant. They don't change over time. So we know how long it takes for potassium to decay to argon. We know how long it takes for uranium to decay to lead, and so on and so forth. So once we had those half-lives measured, and we could figure out techniques to extract the isotopic information, now we have a clock. We have an actual chronometer to get an age of geologic materials, which I just think is crazy cool. All right, so here's an example. Carbon dating. How many of you have heard of carbon dating? Okay, carbon dating sucks for dating rocks. Okay, I'll just tell you that right off the bat. It's great for archaeological materials. It's not good for dating the Earth. But this was the first type of radiogenic age that this guy Willard Libby figured out how to do back at the University of Chicago in the 1940s. This is the age of sort of geologic ages. This is when it was all starting to happen. And so what's happening in the animation, the yellows are carbon-14s, that's our unstable parent, and the nitrogens, nitrogen-14 is the stable daughter. And so you're seeing just sort of a representation of how carbons just spontaneously decay to nitrogens. Okay? There's no saying which one is going to decay when, but we know that it takes about 5,700 years for half of these atoms to change into daughter product. That's our half-life. It's constant and it doesn't change. So what we do is we look at the sample, say it starts with 100% of our carbon-14, which is our parent, and after one half-life, 50% is now daughter material. So the ratio of parent to daughter is 50-50. Well, it turns out no matter which isotopic system you choose, if you find a ratio of 50-50, you know one half-life has passed. And since half-lives have been measured and they're constant, then we know how much time has passed. So that's pretty much what we do. We extract these materials from rocks and minerals. We find the ratio of parent isotope to daughter isotope. We figure out how many half-lives have passed, and then we times that by the half-life of the material, and we get an age. It sounds fairly simple. I mean, there are some complications that we could get into, but I'm not going to get into them now, but it's pretty straightforward. Well, I told you that carbon-14 doesn't work well for rocks. So if we want to get at rocks, we have to pick a system that has a longer half-life than 5,000 years. And that's because 5,700 years, what happens is that you start with 100%, and after not very long, say about 30, 40, 50,000 years, almost all the parent has decayed away. And then it's really hard to measure what's left in the sample. It's too small to get a robust measurement. So it's better to use something like, say, lead. Uranium decays to lead, and it takes about 4.6 billion years. That's the half-life for half the parent to decay to daughter. That's a really good number. Does anybody know why? What's important about that number? That's the age of the Earth, right? So if we want to date rocks that are about the age of the Earth, that's a good system to use. So is this system, rubidium to strontium. That system has also been used a lot to date rocks and meteorites. But it turns out that lead is a great isotope to use. So we're going to talk about lead in particular. And it also turns out that some of the oldest rocks on Earth that have ever been dated come from Western Australia in a place called the Jack Hills. I was lucky enough to have the pleasure of dating some of the grains from these rocks when I was a grad student at UCLA. And the very first one I analyzed, the data came off the machine and it told me it was 4.2 billion years old. And I just about fell out of my chair. I thought, no way. And that was like 15 years ago. Now many, many of these have been dated. So now here's some of the schematics. This is just, again, to show you this decay system. I'm not going to spend much time on this, but we're going to talk mostly about uranium-238, which decays to lead-206, which is very abundant. And it decays with a half-life of about 4.6 billion years. So this is a great system to use for dating old rocks on Earth. There are other isotopes we can use as well, like thorium, which decays to lead, and U-235 also decays to lead. There's a little bit of lead in our samples that's non-radiogenic, and we have to measure that and correct for it, kind of take that out of our measurements so that our ages aren't unusually old. But we know how to do that. We're pretty good at doing that. So now we need a material. We need a material that's going to have these things in it, something that has uranium in it and has lead in it. Well, it turns out there's a wonderful material for this, and it's called zircon. You might know it as cubic zirconium. That's the gemstone form of it, right? Well, zircon is great because it's abundant in rocks that are abundant in the Earth's crust, rocks like this. And I'll have this after the talk if you want to look at it. This is a chunk of granite from up in the Catalina Mountains. If you were to crush this up and look at it under a microscope, it would be chock full of zircon. Zircon is a great mineral because it incorporates an awful lot of uranium when it forms into its crystal structure. And that's because uranium fits in the crystal lattice where zirconium fits. They're about the same size. And once the uranium is in there, it's held tight and it doesn't go anywhere. So now we've got our parent isotope locked into this crystal when it forms. Okay? And as soon as that crystal cools, it's going to start decaying into daughter product. So we've got our clock in place. The other cool thing about zircon is that it does not incorporate a lot of lead into its structure when it forms. That means we don't have excess lead that was there already coming into our crystal. So that doesn't screw up our clock, which is great as well. Again, it's very common at the Earth's surface. It grows at high temperature, so we find it in magmatic rocks, igneous rocks like granites, which are very common on the Earth's surface, which is great. And it has this nice long half-life, so we can look for old material in these zircons. Now, I just want to give a little aside here. This is just for point of interest. Has anyone ever heard of Claire Patterson? Of course not. I know. Claire Patterson is perhaps the most important geologist that ever lived, and nobody knows who he is. He was the first guy to come up with a date for the Earth of 4.55 billion years old. This guy was the first guy to do extensive work trying to figure out how to use lead, the lead isotopic system, to get an age of the Earth. He was the first one to develop what we call a sterile laboratory to do this work because he noticed, as he was working with zircons, that every time he measured their lead isotope composition, he would get wildly wrong numbers, and they were like 200 times more lead than was expected. And he couldn't figure out, why are these things so rich in lead that's not coming from radioactive decay? Where is all this lead coming from? Well, he figured out that it was coming from leaded gasoline. Back in the 1920s, this guy, Thomas Midgley Jr., who worked for GM, discovered that if you put lead in gasoline, it stopped the engine from knocking. Well, you can imagine, right? People went crazy for this stuff. So GM and DuPont and Standard Oil in New Jersey hooked up, and they started commercializing what's called tetraethyl lead. And that stuff is found in everything. It was in toothpaste tubes, it was in water tanks, it was in gasoline, it was everywhere. And lead started to just get spewed into the atmosphere and go all over everything we eat, everything we touch, everything we breathe. Well, Claire Patterson figured this out. So not only was it screwing up his age dating, but he realized that it was screwing up people as well. And he made this sketch, what people's lead burden, so each one of these dots represents lead in your system, what your lead burden was if you were pre-industrial, and what people's lead burden was in the mid-60s after this had been happening for a while, and what you look like if you had acute lead poisoning, which a lot of people got who were working for these different companies. People were dying because of lead poisoning. So Claire Patterson, being a scientist, decided he'd put his scientific brain to use. He went and did studies on ice cores to show that the atmosphere pre-industrial had way less lead in it than the atmosphere post-industrial. And that's because the ice, every year a new layer of ice forms and it traps atmosphere. So you can actually analyze the atmosphere in the ice layers going back hundreds of thousands of years. And he started to lobby these ethyl corporations to say, you guys, this is bad news. We got to stop doing this. Not only is it messing up my science, but it's hurting people. I know the science is really important, but it's hurting people. It's making people sick. So he was pretty much single-handedly responsible for unleaded gasoline and sort of getting lead out of the system. Now, unfortunately, all of us who are alive now have a lead burden more like this because we've been alive through that. We have it in our bodies. And it never goes away, right? It'll be there forever. But he made great strides. Now, the other interesting thing he discovered through his studies was that he couldn't find rocks on Earth that were really, really, really old. I mean, they were predicting they should find rocks that are like at least 3.5 to 4 billion years old, and he wasn't finding that. And he thought, what's going on here? He was one of the first to start understanding that the Earth's surface was always regenerating through plate tectonics, that the Earth's surface things get remelted, they get pushed down deep into the Earth, they come back out as magma, and so those ages are not always preserved, right? They get reworked. And so what he did is he started looking at meteorites. Meteorites, if you remember from Dr. Fleming's talk, are chunks of that primitive solar system when the solar system first formed, at the same time that the Earth was forming. So about 40,000 tons of this stuff falls to Earth every year. You can pick it up, you can grind it up and analyze it and get an age. And that essentially is the age of the solar system, which is the age of the Earth. And as you can see, many, many people have done this with many different samples, many types of meteorites found all over the world. And it's undeniable. The age of the Earth and the solar system comes out to be about 4.6-ish billion years old with great precision. So it's pretty cool, pretty robust. Now, the oldest rocks on Earth, as I mentioned, are from Western Australia. P.S., if you want to hear about this after the talk, those little grains, those little zircons that are 4.1 billion years old, also have trace evidence of photosynthetic life. Yeah. Okay, so earliest life on Earth, probably pre-4.1 billion. Which means the Earth probably wasn't the way we thought it was back then. It was probably very much like it is today, which is pretty crazy to wrap your head around. All right, so now how do we analyze these things? This is sort of the fun part. Okay, so what we do is we take these little zircon grains out of a rock, like this chunk of wilderness granite from up in the Catalinas. We crush that down, we extract some little zircon grains, and we put them on. You can see this after the talk if you want to see it up close. We put them on an epoxy mount, these little zircons, and we put them in a machine and we zap them with a laser, and we get the uranium and thorium out of them and we get an age. Now, what we discovered early on with these studies was that zircons are not very simple. They're super complex little mineral grains. If you look at them, they have cores, they have these concentric growth rings in them. Some of them look really grungy. People used to take these grains and just dissolve them all together and then date them all together, and they would get an age and say, that's the age. And what we discovered was, no, you're getting an age that's a mixture of all these different events that are recorded in that single crystal. So now what we do is we zap them with lasers at very, very small little portions of the grain, and we get an age. So this is the Arizona Lasercon Center at UA. It's run by Dr. George Garrels. It's an amazing place. We take these little crystals. This is what we call a backscattered electron image of a zircon. Every one of these little circles is an excavation pit from the laser that hit the surface of the grain and zapped out a bunch of material. That material then flies down this tube in our mass spectrometer where the different isotopes of uranium and lead are separated based on their weight, and they all go into different collectors and get measured. So then we can say how much uranium is in the grain, how much thorium, how much lead, and we can calculate an age for that grain. Here's some examples of what we found. So here's that first zircon I showed you on this last slide, okay? These are all laser pits on the grain. And here are the ages, the multiple ages that were found from one crystal. Okay, we have a center portion, what we call an inherited core, that's about 130, 140 million years old. We have these concentric growth rings around that, which is basically what magmatic zircon looks like. That's how it grows in a magma. That's about 96 million years old. And then we've even got this very thin rim on the zircon that's 57 million years old. So 3 different events recorded in one crystal that we can get from the single rock. Here's another example. These are all the pits again. Here's the grain. We have that nice magmatic looking center portion. We call it a core. 382 million year old core with an 81 million year old, what we think is metamorphic overgrowth. So not in a magma, but maybe from hydrothermal fluids growing on the rim. So again, multiple ages from one crystal. This is from the wilderness granite right up in the Catalina Mountains. This is a 52 million year old granite. There's our beautiful concentric growth rings. But it also records 2 other cores, 1.7 billion year old core in the middle. So there are rocks up there that are that old, and then a 1.4 billion year old core around that one. So we have 2 episodes that are shown there of overgrowth on that original core, which is pretty cool. But what else can we date? We can date geologic events like mass extinctions. Okay, you've probably all heard of the KT extinction when the dinosaurs went extinct. But there's the biggest extinction in Earth history happened between what we call the Permian and the Triassic period. So this is right at the end of the Paleozoic, right, oldest life, to the middle life, Mesozoic. This is the age of the dinosaurs above. And it just so happens that right around that boundary, all of these fossils that are very prevalent in the rocks below disappear. It's an extinction event. They don't exist anymore. And it also just so happens that there's a layer of igneous rock, volcanic rock, that sits right above that extinction event that we can date using zircons, and it's about 252 million years old. That's great. So now we have a numerical age on a life event that we can see in the rock record. And so we can put those both together and put them on our geologic timescale. And this is how the timescale was constructed. Now, maybe the coolest part, though, is back in the late 50s, these guys, Marie Tharp and Bruce Heesen, were making maps of the ocean floor, and they noticed that in the mid-Atlantic, so here's Iceland, this is the Atlantic Ocean, running down the middle of the Atlantic is a high ridge of rocks. We call it the mid-Atlantic ridge. It's like a mountain range. And on either side of that ridge, they noticed that these magnetic reversals in the Earth's magnetic field were recorded in the rocks. So the rocks that form on the ocean floor have magnetic minerals in them, and those minerals line themselves up with the Earth's magnetic field. And that has reversed many times throughout Earth history. Well, they noticed that this was symmetrical around these ridges. So they started thinking, you know, those rocks are like a conveyor belt. They're moving away from the ridge at a pretty even rate on either side, and that's why we see this very symmetrical pattern on either side. That was really the first spark of plate tectonics. The ocean basins aren't still, they're moving, they're growing, they're expanding over time. So what they did is they sent out these boats that dredged rocks up from the bottom of the ocean. They dated them using these radiogenic isotopes, and they came up with ages of each of these magnetic stripes, and they measured the distance from where the rocks were forming at the center to the magnetic stripe. They had an age, now they've got a distance and an age, and they can come up with a rate of spreading, a rate of plate tectonic motion. That's crazy. So we know how fast the plates are moving based on our age data and the distance to our stripes. So that's what we see here. The geologic timescale is our magnetic reversals and the ages at which they happened. And so that gives us even more precise age data for our geologic timescale. And it was the birth of plate tectonics. So here's the age map of the ocean floor. I know this is a little hard to see, but the continents are in gray. There's the mid-Atlantic ridge running right down that the plate boundary. So on this side, things are moving off to the right, and on this side, they're moving off to the left. The ages are young in red and old in blue. So they're just forming at the ridge, and just like a conveyor belt, they're moving away from the ridge and off to the sides. And this was really the start of the unifying theory of plate tectonics, and it wouldn't have been possible if we couldn't date those rocks. We would have no idea what the rate of motion was. And that gives us things like this, where geologists can actually make models. They can make computer-generated models that show how the continents have moved throughout geologic history. So we go back to 400 million years ago. It's really hard to tell what you're looking at, but when we get to about 250, there's Africa, there's South and North America. Okay, and India is going to break off from here, and it's going to make its way towards Eurasia and form the Himalayan mountains about 50 million years ago. There it goes, making its trek towards Eurasia. That's of particular fondness to me because I did my PhD work here on the Tibetan Plateau. And we can project where we think things are going in the future. So if we were going to be here in 50 million years, it would look something like that, but I don't think that's going to happen. All right. Now, the last thought I want to leave you with, because I know we're running low on time. The final thought, the geologic timescale, it's well established. We have all these wonderful things through geologic history that give us a really nice picture of Earth history. We know the age of the Earth. But some scientists are proposing that now we are in a new geologic epoch that they're calling the Anthropocene. Remember that our geologic epochs and periods and eras are defined by life, changes in life, and the things that life do to interact with the Earth. Well, humans are interacting with the Earth in some pretty intense ways, right? We know this. Our population has increased tenfold since 1700. We're on the path towards 9 billion people in the next 30 years or so. And people produce a lot of stuff, a lot of trash, a lot of plastic, a lot of garbage. And that stuff stays on the Earth. So we dispose of it, and it stays where it lies. We also have become better at moving around Earth materials like sand and dirt than any other natural process on Earth. That's right, so we move more sediment than rivers, ice, wind combined. We move more stuff. We are the excavators on this planet. And of course, our garbage is everywhere. Well, what we're discovering is that our garbage is now being recorded in the geologic record the same way that a fossil would be. I'm serious. Our trash and our plastic are now part of the geologic record. Here's an example. There is a new rock that scientists have termed plastiglomerate, like conglomerate. It is rock that is made up of rock material and plastic material, and you can see even in these pictures, they're little sediments of plastic. I've seen this, I've witnessed this for myself on beaches in Hawaii where there are little different colored, what look like sand grains, but when you pick them up and roll them through your fingers, you realize that they're pieces of plastic that have been out in the ocean, they've been weathered and rounded, and they've come up onto the beach, and they find their way into rocks. They also find their way into animals that eat things off the beach, and so we're starting to find seabirds that when they die, their entire stomach cavities are just full of plastic. Yeah, so we're having a very lasting effect on the planet. I mean, aside from climate change, also a physical effect. And what's interesting about this is that scientists are sort of arguing about, well, what are we going to use to mark the beginning of the Anthropocene? And they define the Anthropocene as the geologic time period in which humans have had an impact on the planet. And they talk about many different things. Maybe it's the atmosphere, CO2 in the atmosphere, right? So post-industrial revolution, we can measure atmosphere in ice cores. Maybe that's the start of the Anthropocene. Maybe it's when humans started farming. We see different seeds in the geologic record that didn't exist before widespread agriculture. Maybe that's the start of the Anthropocene. But a lot of scientists are converging onto this idea that this is the marker in the record of the Anthropocene. It's a physical marker that will be left behind long after we're gone, which is our trash and our plastic. So now if we put this all together, we look at this sort of full-on geologic timescale going all the way back to the formation of the Earth, which we know from the ages that we've gotten from meteorites, and sort of working our way down. Here's our oldest little zircons that come from Western Australia, right around 4.1, 4.2. And actually, we should amend this to show that there's evidence of life as well here. Traditionally, we think of earliest life as sort of early Archean, sort of 3.8 billion, but we know it's a little bit older. And we work our way all the way down to today. There's humans. They take up 0.1% of the geologic timescale. So we are less than 0.1% of the geologic timescale. I know we think of ourselves as very important, but we're very tiny in terms of the Earth history. Dinosaurs are about 5% of Earth history, and we're about 0.1%. And I will close with that, and I just want to leave you with this. If you're interested in sort of where we're headed and these ideas of change and how the Earth is changing and how humans are affecting it, please join us at Centennial for Earth Transformed, which starts Monday, the 25th. And I've had such a good time with you guys. You're such a gracious audience. Thank you for having me.
So we're now at the Science Cafe portion, which means we get to hear from the audience. So we'll basically, Barbara Consales, who's also with the Dean's office over here, she's waving her hand in the back. We're going to try to work the crowd, both sides, and get to your questions. We do know we're extending time, but we've gotten feedback that you're okay with that you actually want to hear the content. So we do also want to be mindful of our presenters' time and yours as well. But why don't we start?
I got nothing to do. I got kids at home, so the longer I'm here, the better.
So basically the protocol is, by a show of hands, we'll get to you as we can, and as we determine are the questions, we'll ask you to take the microphone, pose your question, and then hand back the microphone, because sometimes we end up in a conversation with one, and we want to give more people a chance. So let's just, by a show of hands, any questions for our speaker right up here?
Yes. No, that's right. So that's what the granite, the intrusive granite is the 1.4. Yes, and the Vishnu is older. Absolutely correct. Yes, and the 1.4, an interesting side note, there are granites in the Catalinas. The Oracle granite is also 1.4 billion. It's the same age as that Zoroaster granite in the Grand Canyon. So we think they were happening at the same time. Yeah, thank you.
Okay, so we're going to actually hand you the microphone to the whole audience. So Barbara's making her way to this gentleman.
Thank you. Good question, Karen. So my question deals with the Earth's reversals, magnetic pole reversals.
Oh boy, okay.
Is that
You're going to test me because that's not my expertise, but I will try.
Perhaps not an appropriate question.
Yeah.
So as the poles degrade and reverse,
yeah,
there should be a concomitant decay and collapse of the radiation belts. Mm-hmm. And as that happens, all the radiation which we're protected from by Van Allen and other sorts of belts collapse until the new polarity is established.
Right.
Is there now a correlation established between those reversals and the magnetosphere collapse and the radiation belt collapses with extinctions of any sort?
That's a great question. So this is something that scientists have been postulating for quite a while, that maybe magnetic reversals are related to mass extinctions. And I will say that there is some evidence that there may be relation with some, but not all, and that there is stronger evidence for other things to have driven the great mass extinctions. And so in particular, the KT extinction, we've all heard about the large asteroid impact. There's a multitude of evidence that is the thing that triggered. Now, it may not be the only thing, because we think there was also enhanced volcanic activity at that time, which changed climate and all of that. But there isn't, to my knowledge, there isn't any definitive, when the pole, that's what triggered the extinctions. And it's also still in question how fast that reversal happens. We don't know yet. Right? I mean, some people say it's almost instantaneous in terms of geologic time, like maybe hundreds of years, and other people think maybe it takes thousands to millions of years. It's really hard to nail that down. So that's a really good question that I can't give you a better answer than that.
I'd like to follow up on that and ask how often that happens, and is it regular?
Yeah.
And if it's regular, are we ready
When's it
for another
happening
one?
again? Should we all brace ourselves? Yeah. Well, no, it's true. I mean, people predict that there may be another one coming up soon. Of course, if you look at the geologic time scale, you can see it's not what I would call absolutely regular, right? I mean, look at here. We've got some that are really, really long periods of normal and reverse, others that are really, really short. So it is cyclical in some sense, but there is no magic number. Right? Every 10 million years it reverses. So let's get ready for the next one. We can't really say. And we don't really know what causes it either. But people are nervous about it because, right, we know what the magnetic field does for the Earth. It deflects the solar wind. All that charged stuff that the sun is shooting out of it that could really cause serious damage to us is being deflected by the magnetic field. So if there is a period of time where the magnetic field is actually shut down somewhat, that could be really bad for things that are living on the planet. We don't really understand it that well. Yeah.
Next question. Here in the front. I could probably get there faster. Hold on just a second so we can have the whole audience here.
Yeah. So the question is, a reversal is actually a 180 of the magnetic poles. That's right. So what is today north versus south, what's positive at the north and negative at the south, completely flips. So we get negative at the north, positive at the south. Yeah. And so we see it in the minerals. The minerals tell us that it happened, but we're not sure why. Yeah.
Also, what about the tilt of the Earth? I know the moon stabilized the Earth,
yes,
but we still have about a 1 degree shift, which really increases the weather.
Right. About 1 to 2 degrees. It happens over about every 11,500 years. This is one of the, what we call the Milankovitch cycles that drive the ice ages on the planet, right? So if you imagine if the Earth didn't tilt at all, right, if it was perfectly vertical, so the geographic North Pole was straight up, the sun's coming in, say, from my right, then you wouldn't have seasons because that distribution of sunlight is always the same. It's always direct at the equator and it diffuses toward the poles. But because the Earth is tilted, The northern hemisphere, when it's toward the sun, is in summer, right? When it's on the other side of the sun, it's away, so it's winter. Well, the extent of that tilt affects how extreme those seasons are. So the more tilted it is, the more extreme the seasons, and the less tilted, the less extreme, the less difference there is between winter and summer. And it does, it change, and that one, the cycle is really well nailed down. And so we know where we are at any given time in that, what we call the precession. The Earth kind of wobbles. So we are, right now, we're sort of at the maximum of where we are in our tilt, and we're gonna come back up a little bit, and then it's gonna flip-flop in about another 10,000 years or so-ish. Yeah, none of us have to worry about this, right? But it's really interesting because we can map that going back through time, which also, we can also see a correlation to the shape of the Earth's orbit. So right now, fun fact, just if you're bored, just tell me to shut up, but the Earth's orbit right now is almost a perfect circle, okay? So that means that summer and winter were almost the same distance from the sun, right? So that doesn't cause seasons, by the way, if you didn't know that. Some people think it's the distance from the sun. It's not. But there are times where the Earth's orbit becomes more like an egg shape, an ellipse, and then there are much more extreme differences in the distance between the Earth and the sun, and that can also influence the extremity of the seasons. So there's multiple things that go on with the Earth over hundreds of thousands of years, and that cycle for ellipse shape is 100,000 years. The angle is about 23,000 years, and then the flip-flop of the angle is about 11,000 years. And those combined together match the ice ages back through time. We can actually map when those things changed and when we've had ice ages, and they match perfectly. They're beautiful. It's a beautiful data set.
Okay, give me just a second, I'll get up there. I'll just ask you guys to pass this down.
Is there any evidence that the Milankovitch cycles that you're talking about now go back previous to the Pleistocene, or how far can you prove that they go back? Evidence.
Well, I can't prove it at all because I don't work on that stuff. But that's a really great question. It's a great question. I'm not sure exactly how far back those cycles are recorded. I'm really not sure.
So you have some homework.
I have some homework. That's right. That's right. I do have some homework. But we know, I mean, we have a record back a couple million years because we, you know, in terms of the glacial cycle, but I don't know beyond that. Yeah, right.
Other question?
You guys are easy on me tonight.
Well, I always have a question.
Yeah.
We get to work with undergraduates and graduate students, and Jess is just one of many but excellent teachers in addition to being a great research university, right? And so I always like to hear, how did you get involved and interested in geosciences and to pursue the career you have?
Okay, so I'll keep it short, but the long short story is that I was an English major and wanted nothing to do with science and thought that I could not do it, and I was a writer and all that stuff. And then I took an introductory geoscience class when I was an undergrad at Syracuse University, and I saw all these slides up on the screen of the Grand Canyon and the Himalayas, and I went, I want to do that. Whatever that is, I want to get in on that. So the power of mentorship plays in here because I went to the geology department and there was a woman who was the department head, and I said to her, look, I have very little math and science background. I'm terrified, but I really want to do geology. Can I do it? And she looked at me and she said, do you want to do it? I said, yeah. And she said, then you can do it. Go enroll in pre-calculus and physics and chemistry and do it. So just do it. So yeah, woo, that's right, do it. So I did, and that was it. And then I discovered when I was a graduate student at UCLA doing this really exciting work in the ion probe laboratory, doing these extraction, you know, using laser beams to, well, it was an oxygen beam, but extracting age data from these zircons. I realized that as much as I love the research, I really love teaching. I started teaching when I was a grad student, and it just was kind of the thing that clicked for me. So my job at U of A is primarily teaching, and I teach the classes, and I used to teach in Centennial Hall, so I think my largest class was 980 students. Yeah, and my smallest class is about 150. That feels really tiny to me. So you guys would be a small class to me.
But I do want to add some really interesting elements. Jessica has researched how to best ease and open the minds of students as they're coming in, because a lot of non-science students aren't necessarily receptive, right? So having a quartet or music playing as students has been proven to open the mind and ease the learning. And
well, I don't know about proven, but we did an experiment my first year in Centennial, where my TAs and I played guitar for the students as they were coming in. And so I think they saw me as more than just the science teacher. And as a side note, I will say that in particular, my anecdotal evidence is that females get more excited about science when their teacher comes in a nice outfit. So I get more comments. I get more comments from my female students. Your class was the best class ever, and I really appreciated the way you dressed every day. And I thought, okay, well, it keeps their attention. That's all I care about. So
well, and you hear of such a large lecture class, how can students really absorb? But they've also developed a system where you're doing small group activities in that larger audience. So all kinds of approaches to open this world of science. And we do have a question. So
tell us more about Tibet.
Oh, I love to talk about Tibet. What can I tell you about Tibet? I will tell you, so my book isn't published yet. If any of you know any publishers who want to publish a book about my trip to Tibet. So my favorite part to tell about Tibet was that I fell into the experience. I went to UCLA, my advisor had a grant to do work in Tibet, and he said to me, I want you to go. He had some rocks in his outer office that we started dating, and we went, oh my gosh, these rocks are really cool. And he said, I want you to go get more. And there were a group of male students who were going, and my advisor said, I want her to go with them. And their advisor said, no way, she can't go. She's going to slow them down. She's going to get sick. And what are they going to do? They can't take care of her. And my advisor said, well, she can take care of them while she's there doing her geology. It was kind of like that. So I went. My first summer, I went for over 100 days. And we lived in tents out in the middle of the Tibetan Plateau, a 5 to 6 day drive from Lhasa, which is the capital city, which is at about 12,000 feet elevation. We worked at an average of about 15,000 feet. I did not take a shower for 3 months. We lived then, you know, it was that kind of thing. It was a hardcore experience. And then add to it that I was the only woman in the group. All of our drivers were male Tibetans. We had Chinese colleagues that interpreted for us as well as traveled with us, because in China, you're not allowed to go anywhere without a Chinese colleague. It's a communist country. And then some male graduate students from UCLA and myself. So the book is about my journey, sort of as a girl who came from, you know, the suburbs and didn't think she could do science, to being on the highest plateau on Earth, doing geology with some of the best scientists in the world. And just as a side plug, my husband now was one of them at the time, and he is one of the brightest minds in geology today. But if you're interested, if you find him through the College of Science, Paul Kapp, he's now doing work that are so tiny that they're carried by wind, and they travel across oceans, and they get deposited in Asia by wind. And then you can tell about wind patterns, and you can learn about wind excavation of mountains by dating these little tiny zircons. So that's all stemmed out of that work. But when I was in Tibet, I worked on a mountain range that was formed by a fault. It looked very similar to the Catalinas. Right? So if you're familiar with the Catalinas, that tabletop that you see on the front that looks like this, that's because the Tucson Mountains used to be up on top of the Catalina Mountains, and they slid off over a period of millions of years. That's called a normal fault. I worked in a mountain range like that in southern Tibet, and so I collected the granites, just like these granites, and I dated them, and I tried to reconstruct the history of that mountain range. It was very similar to the Catalinas. So I have a love for that kind of geology. Yeah. It's a beautiful place to go. If you've never been, go to Tibet. It's amazing.
well, let's give Jessica a round of applause for her talk. As I mentioned earlier, she is happy. She has some great samples, and you can ask some one-on-one questions. I just have one last announcement. So those of you that enjoyed tonight's listen to me, presentation, and are enjoying the series,